Hi guys, so this is a question on momentum. Right, that's a paper from Cambridge 9702, paper 21, May June 2024. Right, state the principle of conservation of momentum. Right, the principle of conservation of momentum states that, right, it states that for an isolated system, total momentum before collision equals total momentum after collision. Right, when we say a system is isolated, we mean that there are no external factors or forces acting on that system. So if you don't highlight that this is an isolated system, then it means you're not going to get all the 2 marks. Alright, so you have to indicate, if you just say total momentum before collision equal total momentum after collision, and you don't highlight that this is an isolated system, then, or you can say closed system. Isolated or closed system is still the same, right? So this has to be clear that it's a closed system and there is nothing else affecting that whole system. Right, now let's move on to part B. An object of mass 2m is traveling at a speed of 5 meters per second. I'm sure you can see that from the diagram. In a straight line, it collides with an object of mass 3m, which is initially stationary, which means the initial velocity of object B. So you can call this object A or object 1, and then this is object B. Alright, we have the initial velocity, so we have UA equals 5.0 meters per second. The mass of A is equal to 2m, and then we have UB there is equal to 0 meters per second, and then mass of B is equal to 3m. It's always good to highlight that. All right, okay, after the collision, the object of mass 2m, which is A, moves with a velocity v. So that means the VA is equal to V after collision at an angle of 30 degrees to its initial path. Right, that is good. Okay, the object of mass 3m moves with a velocity w, so that means VB after collision is w. Awesome. Meters per second. Meters per second. Meters per second. This is a very interesting question. All right, so this is where we are. Okay, so what it means now, for us to answer this question, we need to apply some conservation of momentum, and probably, and I don't know what the question wants down there. Okay, by considering the conservation of momentum in 2 dimensions, calculate the magnitudes of V and W. So in my mind, I'm thinking of forming simultaneous equations, but I don't know how we're gonna produce those. But let's make sure that we try and resolve this. If you come across anything like this, that means we need to deal with the resolution of things here. But at the same time, we have to highlight also that okay, the aspects of conservation of momentum, of course. So let's assume this is the original path, that's before collision. All right, so before collision, we know we're going to have right, that means, right, before collision we have UA plus MB UB. Right, so if you look closely, this is actually giving us what, 2m times, right, 5, and then plus 0, of course, so which means we have 10m. Right, So this is total momentum before collision, right? And then after collision, what we need to appreciate, all right, this is object A and this is object B. So object A, we need to resolve the momentum of object A horizontally and vertically there. So we have, right, two momentums, the momentum of A and the momentum of B. Right, remember momentum is mass times velocity. But at this point we are going to apply some resolution. So the velocity component is being resolved at a 30-degree angle for both of them. Alright, so we also have some vertical component and then also another vertical component downwards, of course. Right, so for object A, we know the momentum is 2mv in that direction, and then in this direction this one will be 3mw. But then if you look at the horizontal component, that means for object A we have 2m, right, v cos 30. Then for the other one is 2mw cos 30. Right, then for the vertical component, this is 2m v sine 30. Then downward we have 3m. Okay, I made a mistake there, it's not 2m, this must be 3m. Right, sorry about that. 3mw sine 30 degrees. All right, this is very interesting, quite interesting. Right, so we're going to apply the law of conservation of momentum in both directions, that is horizontally and vertically. Right, so let's consider the vertical components. Right, consider the vertical components. Right, we must appreciate that before collision there was no vertical collision, so we didn't have any components vertically. So which means before collision we have zero momentum being equal to. So now when you look at the collision after after the collision, then you see the vertical component of object A is 2mv sine 30, then for object B is 3mw sine 30. So that means we'll have those subtracting one another. So this is 2mv sine 30 minus 3mw sine 30. Then I'm sure we can see that we can actually factor out sine 30 and m here. So f0 is equal to, right, m sine 30. That means we have 2v minus 3w. Right, dividing both sides by m sine 30, that means we have, right, 0 is equal to 2v minus 3w. Right, this we can call it equation number 1. All right, and then after collision, consider the vertical components. So here we are using the law of conservation of momentum. This is momentum before collision, this side, and then this is after collision. All right, that's the vertical components. For the horizontal components, right, consider horizontal components. Right, the momentum before collision, it was, if you go back there, it was 10m, if you remember very well. So we're having 10m being equal to, now if you look at those two, they're actually in the same direction. So 2mv cos 30 and 3mw cos 30, we are adding them. So that means we are saying 2mv cos 30 plus 3mw, right, plus 3mw cos 30. All right, and then from here we can see we can get rid of this. This is gone, the m's are gone there, so that means we have 10 being equal to, what is cos 30 by the way? Cos 30 must be root 3 over 2, or is half, I'm not sure. Root 3 over 2. Okay, super. So this is 2v times root 3 over 2 plus 3w root 3 over 2. Alright, so we can deal with this nicely. Right, 2 goes there, 2 cancels out, so you have 10 being equal to 2. So that means here we have root 3 v plus 3 root 3 over 2 w. Right, this is equation number 2. Okay, so now from here I'm sure we can see that we are solving some simultaneous equations, right? Let's check from the side. Right, we can say that from equation 1 we can make maybe v or w the subject of the formula, right? So that means v 2v is equal to 3w divided by 2, so v is equal to 3w over 2. So let's come to that one and substitute this into that. Right, 10 is equal to root 3, right? So this is 3w over 2 plus 3 root 3 over 2w. So we still get the same thing here. I'm sure you can see that 3 root 3 over 2w and another 3 root 3 over 2w. So that means it's right, 3 root 3 over 2 times 2 actually. 3 root 3, right, all over 2 plus another 3 root 3 over 2, that's times 2, right, times 2. So we get 3 root 3, right? So 10 is equal to 3 root 3 w. Right, my space is no longer enough, I'm gonna come down here, right? So dividing 10 by 3 root 3, we get w. So that's w, and then v will be equal to 3 over 2 times 10 over 3 root 3. Right, simplifying these, what do we get? Right, the first one is 10 over 3 root 3. I am getting 1.9245, which is approximately 1.9 meters per second. Right, and then for the second one, that is 3 over 2. Right, 3 over 2 times 10 over 3 root 3. Right, what do I get here? That's 2.886. 2.88675. That's approximately 2.9 meters per second. Right, this is what we have. Right, I hope we got the solutions here. All right, let's move on to the next one. An object of mass 4.2 kilograms is traveling in a straight line at a speed of 6 meters per second. This is an object traveling in a straight line. Okay, the object is brought to rest in a distance of 0.05 by a constant force. Calculate the magnitude of this force. Alright, this is quite interesting. Very interesting. Right, what's the kinetic energy of this object? Right, EK or KE is equal to half mv squared while this is in motion. Alright, so what do we have here? Half of the mass, which is 4.2, times the velocity, which is 6 squared. Then what do we get here? 0.5 times 4.2 times 36. Right, I'm getting 75.6 joules. Right, this is the kinetic energy that this object has. So work has been done to stop this object by a force, right? So we know work done is equal to force times displacement, which is distance there. And then that means force will be equal to the work done over the displacement, right? But the work done in this case is actually equal to kinetic energy. We're assuming that, right, all the energy that was, I mean, conservation of energy, the law of conservation of energy here. So that means we have 75.6 over 0.05. What do we get here? Divided by 0.05 equals 1512, which is approximately 1500 newtons. Okay, there's a unit there, no need to put that. I hope you understand this, right? This thing at kinetic energy, oh, sorry about that, half mv squared, this was 6 squared there. This thing at this object at kinetic energy, right? Right, let me take it back. You can see some things there. Equals. Alright, that's good. The object had kinetic energy, and then all of a sudden it was brought to rest. So which means all the kinetic energy was actually countered by the force. So force was applied to stop. So the force was doing some work against, yeah, the like the kinetic. So work done is being converted, kinetic energy is being converted to work done, whichever way you may think of it, but that's how we can actually think around this object, I mean this question. Oh, that's quite interesting. All right guys, so I'll see you next time. All right, goodbye.